Hello students, it's Dr. Sansom here for your pre-lab lecture for experiment 11, which is determining an activity series. This is, as you may know, the last experiment of this semester, so I hope you enjoy it and learn a lot. Today we're going to be talking about oxidation and reduction and how those are related to an activity series, which essentially ranks elements based on their reduction or oxidation potentials. We're going to be talking about an electrochemical cell, even though during the experiment we're not going to construct an electrochemical cell. That would be a logical next step from the data that you will collect. So we'll ask you about that and also about how the cell potential can relate to the spontaneity of the reaction, or the delta G. So first, what do we need to know about redox reactions? Redox reactions involve oxidation and reduction. They always happen at the same time because oxidation is losing electrons and reduction is gaining electrons. And so if the electrons are lost from somewhere, they have to be gained somewhere else. So that's why we often say redox instead of sort of spelling out oxidation and reduction. And this is important because when elements undergo changes in their oxidation state, they will have different properties. For example, in this experiment, we're going to be looking at metals, solid metals with a zero oxidation state, becoming aqueous ions. And of course, you can't have like a stick of ions because they're all the same charge. They would repel each other. So when you have an ion, that's going to be dissolved in the solution. So some of those sort of details about the way that we write the symbols in our chemical equations really matter a lot in terms of what that physically is going to manifest as. In any case, oxidation and reduction are opposites of each other. So if you lose electrons, that's oxidation. If you gain electrons, that's reduction. But you also see situations in more complicated reactions where an element will gain oxygen by making more bonds to oxygen than it had before, or lose hydrogen by not having bonds to hydrogen that it had before. And also the oxidation number could increase or decrease. Now let's talk about a typical electrochemical cell. In an electrochemical cell, what we've done is separate out the oxidation that's happening over here in this beaker on the left and the reduction that's happening over in this beaker on the right. And in order to do that, we have to connect the beakers by a salt bridge, which allows ions to travel from one side to the other, usually something like KCl or just a salt of some kind that's going to balance out the charge. And they also have to be connected, the electrodes here have to be connected by a wire that allows the flow of electrons from one side to the other. So even though the two half reactions, I should say, are happening in different beakers, the beakers are actually connected together, and that's why the reactions are able to happen. In this experiment, we're not setting up our own electrochemical cell, but we use electrochemical cells to measure the reduction potential of different metals and to compare them to each other. Now, I want to point out something that's happening here at the molecular level. So for example, in this beaker on the left, we've got the anode here, which is made of zinc metal. And at the anode, oxidation is occurring, which is the loss of electrons. So we see this half reaction that we could write. Zinc solid makes zinc ions plus 2 electrons. Well, what does that physically mean? The actual mass of our electrode is going to decrease as zinc metal atoms become zinc ions in solution. So we'll have an increased concentration of zinc ions in solution and a decreased mass of our electrode as this reaction proceeds. The opposite is true over at the cathode where reduction is occurring. Here we're gaining electrons, so our copper ions that are in solution will gain electrons and become copper solid. So this electrode will actually increase in mass. The copper ions that were floating around in solution will stick to the surface, gaining the electrons that have come through the wire from the anode. And likewise, our concentration of copper 2 ions here will actually decrease over time because they will precipitate out as copper. So this is a typical voltaic cell or electrochemical cell where the two half reactions for oxidation and reduction are separated. There's a couple of helpful things to remember here, just to keep things straight in your mind. One of the challenges with electrochemistry is that it's like a 50-50 chance all the time. So losing electrons is oxidation, gaining electrons is reduction. We can remember this with Leo goes grr, Leo the lion. Lose electrons, oxidation, gain electrons, reduction. We can also remember an ox goes walking with a red cat. That helps us to remember that oxidation occurs at the anode and reduction occurs at the cathode. And you can remember because you might be able to have a red ox, but you can't have an cat. So this is one way to just keep that straight in your head: oxidation at the anode, reduction at the cathode. Now, one of the tools that we use when we're talking about redox chemistry is a standard reduction potential table. And you'll see a variety of these in Chem 107 and Chem 106, where they have a bunch of different reactions written. But there's some things that are generally in common. So the most important one is that these are reduction half reactions. So you'll notice if you look at all of these reactions, in every case that's listed here, something is gaining electrons, and that is reduction. The other thing that you'll notice is that they have this E0 value, or standard reduction potential value. And these can be positive, they can be sort of large, they can be negative and sort of large. They range kind of between -4 and +4 for most reactions that we're going to see. And they tell us how likely something is to be reduced or gain electrons. And the higher up they are here, these are sorted from most positive E0 values to most negative E0 values. The higher up they are, the more likely they are to proceed spontaneously this way. If our E0 value is positive, or if it's higher than the other one that we're comparing it to, then it will proceed spontaneously this way. All of the reactions that are written here are reduction half reactions. So that means if we have a redox reaction happening, we also need oxidation, and we would pair one of these as written with another one, someone lower down, that wouldn't happen as spontaneously in this direction and therefore would happen in the reverse direction, and that would be our oxidation. So if we need an oxidation half reaction, it's just what's written here but in the reverse. And when we write them together, the net ionic equation would include both reduction and oxidation, so we would add those together, and our electrons would need to cancel out. Okay, last thing with this is that we can use it to calculate the cell potential, and this is important because it's related to spontaneity. It turns out if we have a positive cell potential, then we have a spontaneous reaction. So when we compare our cathode and our anode, or the reduction and oxidation reactions, if we come up with a positive cell potential, then we know that reaction will occur spontaneously the way that it's written. Let's do a practice problem to see how this plays out. So we're going to write the reaction for an electrochemical cell formed by iron and zinc, and then we're going to try and calculate this cell potential. We'll find iron here. We've got iron and we've got zinc. Now, which one is going to be reduced? It's the one that has the more positive electrochemical cell potential, or reduction cell potential, given in this table. And that's our iron. So our iron is going to be at the cathode, and it's going to be the reduction half reaction. And we just write it exactly how it is written in the table. For our oxidation half reaction, we're going to look at our zinc, but we have to reverse this reaction because it's going to go the other way. So we've got zinc solid, make zinc 2 plus 2 electrons. And our overall reaction, we add those two together, our electrons cancel out. We've got iron ions, zinc solid, zinc ions, and iron solid in the product. Our cell potential is just the cathode minus the anode from our reduction, from our table of standard reduction potentials. So we've got minus 0.45 for our iron and minus 0.76 for our zinc. So we do cathode minus the anode. Notice this is almost always the case that you have a minus a negative, so it becomes a positive, right? and then we end up with plus 0.31. So that is, because we have that positive cell potential, we know that that reaction would occur spontaneously. Now, what if the half reactions weren't separated? And you're asked to think about this in your lab report. What if we weren't separating them and we just wanted to know, which things do I mix together? Should I mix iron metal with a solution of zinc ions or zinc metal with a solution of iron ions? Well, we did figure out our spontaneous overall net ionic equation that we had here. And this gave us a positive E0 measurement, which tells us that that's a spontaneous reaction. So we're looking for iron ions, that's Fe2 plus aqueous, right, with zinc solid, which is our zinc metal. So if we wanted this reaction to occur spontaneously, we would want the zinc metal in a solution of iron ions. Another way to think about this, if we look at the reduction potentials, we know that this iron one is higher up, so this reaction should happen spontaneously, which means we want our iron ions to be there in the reactants, and we'll be forming the iron solid. So that's another way to remember, whichever one is happening at the cathode, whichever one is higher up happening at the cathode, those are the ions that we would want in our solution. And when you do this in the reaction, you're going to observe changes happening. This is zinc and copper, so zinc metal in a solution of copper ions. And what's happening is the electrons are moving from the solid zinc to the copper ions. The copper is then precipitating out. It's sticking as a solid to the surface of the piece of metal, and the zinc goes into solution. And what you'll see when this happens is that you'll see a precipitate forming on the surface of the metal. You might see some bubbles. It might get warm because it's common for it to be exothermic. And this is what you'll observe in your experiment. The last thing that we want to talk about today is free energy. So both delta G and E0 relate to spontaneity. And the equation that we use to relate them is delta G equals negative NFE. So just looking at the equation, if we want our delta G to be negative, that means we want our E0 or our cell potential to be positive. So anytime we have a positive cell potential, that's going to mean a spontaneous reaction, which is like our negative delta G. E is our cell potential. That's what we calculated in the previous part, where we were just looking at the reduction potential tables. F is Faraday's constant, and N is the number of moles of electrons transferred in the balanced chemical reaction. So in the example we just did, that would be like 2. And this is the value of the Faraday's constant, 96,485 joules per volt mole. You sometimes see it written as coulombs per mole, but that's the same as joules per volt mole. And that's how you calculate delta G. So the last two things we have are safety and our schedule for the rest of the semester. For safety, make sure you're wearing your PPE for this reaction. The solutions that you're using are skin and eye irritants and made with some acid, so they can burn you, so you should be careful with them. And you should keep the chemicals away from food storage locations and avoid contact with your skin or eyes. The magnesium metal that you're using is a combustible metal, so you want to keep it away from any heat or flame sources. We talked about that earlier in the semester when you did a different experiment with magnesium ribbon, but just be aware of that. Don't light it on fire. Okay, this is the schedule for the rest of fall semester in 2020. If it's a different semester, check with your instructor, but all of these things will be coming up. For fall 2020, the midterm exam 3 will be after we finish experiment 11, open during the week December 7th through 10th, and there will be an exam review during class on December 7th and December 9th. And the final exam will be offered only on December 17th, just for a single day. It's open 24 hours that day, but just on that one day. There will be an exam review on the reading day, so look for an announcement about that. The final exam is optional, so if you're happy with your scores on the midterm exams, you don't have to take the final exam. If you do take the final exam, it can replace a low midterm score, and there's no penalty for taking it. Even if you fail the final exam, it would just get dropped. So it doesn't hurt you to take it, but it may help you. Finally, there's a couple of extra credit opportunities, the TA evaluation and course evaluation. So check those out. And that's it. Congratulations. You made it to the end of Chem 107. It's been a great semester working with you. I hope you've learned a lot, and I hope you have a great day.